Okay, today we're going to talk about the last new topic in Chapter 6 that we will deal with, and it is logistic growth. And after this, we will have our test. So after practicing this concept, we will be having our test on all of the integration techniques and logistic growth. So last year in AB Calculus, you talked about exponential growth. And exponential growth, if you think about what an exponential function looks like, it would look something like this, where you start at some point and it keeps on growing. Well, when you talk about population can't grow unconstrained. There's a point at which the environment can no longer support more people or more animals or more whatever. So there's some kind of constraint, and that's where logistic growth comes in. Logistic growth begins exponentially, as you can see here, and then it changes concavity, and it becomes more like a logistic function, because that it approaches some maximum place for which the environment can sustain the population. And so that's called the carrying capacity, and that is the amount of population that can be supported by the actual environment. Okay? First of all, before we get any further, I have a typo. In this logistic growth differential equation, I was going to go back and change it in my slide, but I didn't want to forget to change it in your notes. So that should be 1 minus P over M. So the logistic growth differential equation is given here, but I want to point out a couple of things. First of all, your initial population is going to be here, so it's your y-intercept. This point of concavity change, or inflection point, your inflection point is actually when the concavity changes, and that happens at half the carrying capacity. And what they like to ask is, when is the population growing the fastest? And the population is growing the fastest at half the carrying capacity. So when it's changing, or when the population is growing fastest. So that happens at half the carrying capacity. All right, so our logistic differential equation is dP over dt equals Kp, so K is some growth constant, times the quantity 1 minus P over M, and M is your carrying capacity, P is your population, K is your natural growth rate, which sometimes you have to solve for, okay? You might be wondering, why are we talking about logistic growth equations, or differential equations, when we've been doing integration this whole chapter? And that would be a legitimate question, except in order to solve a logistic differential equation, we learned integration, partial fraction decomposition, as a method of integration. So you're going to see where that comes from. The good thing is the AP test is not going to require you to show how to go from the logistic growth differential equation to your logistic growth model. You're allowed to just memorize that. But I am going to take you through it so you can see where it comes from, and if you got stuck, you could actually conceivably come up with a formula if you needed to on the AP test, although I don't know that you would want to take the time to do that. All right, this is going to take some space, but we start with our logistic differential equation, and in order to solve it, I have to get the variables on one side. So I need all my p's on one side. I don't have any t's, so anything that's not a p needs to go on the other side. So the first thing I'm going to do is I'm going to rewrite this right-hand side. I'm going to say this is Kp times the quantity m plus p over m. So that's getting a common denominator of m. And then I'm going to factor out the m. So I'll have Kp over m times the quantity m plus p. And now I'm going to distribute the p. So I'll have K over m times the quantity mp plus p squared. Oops, except I forgot to change that to a minus sign. I'm not starting again because I've already started again once. So these should all be minus signs. Sorry about that. Okay? So, what I now have is dp over dt. I'm going to move this over. dp over dt would equal k over m times mp plus p squared minus p squared. And you'll notice that my p's are here. There's an m with that p, but m is carrying capacity and that's just a number, so that's not going to affect anything. So I can go ahead and separate my variables. So I can say I have dp divided by mp minus p squared equals k over m dt. And now in order to solve this, I have to integrate both sides. Well, first I need to factor this in order to integrate. So I have dp over p times m minus p equals the integral of k over m dt. So this is where partial fraction decomposition comes in, because the only way to integrate this is to separate that into two separate fractions. So I have really 1 over p times m minus p. That would be a over p plus b over m minus p. Multiplying through by the common denominator, I get 1 equals a times m minus p plus bp. So if I let p equal 0, I'll get rid of the b. And if p is 0, I get 1 equals am. So a would be equal to 1 over m. If I let p equal m, that'll get rid of my a term, so I'll get 1 equals bm. So b would be 1 over m. So going back to my integral over here, I have the integral of 1 over m over p plus 1 over m minus p dp equals the integral of k over m dt. So you'll notice that I have a 1 over m really kind of in everything, so I'm going to factor that out. So I'll say this is 1 over m times the integral of 1 over p plus 1 over m minus p dp equals 1 over m times the integral k dt. Now that's quite helpful because I can get rid of the 1 over m since they're on both sides. And now I'm able to integrate. So if I'm integrating with respect to p, this is going to be a natural log of the absolute value of p. And because I'm integrating with respect to p, this is going to be minus, because the derivative of m minus p is a negative 1. So I'm going to have, okay, so when I do the integral of 1 over m minus p with respect to p, that means it's the natural log of m minus p times the derivative of negative p. So that's why it's a negative natural log of the absolute value of m minus p. Equals, and I'm integrating with respect to t, so this would just be kt plus c. Now I'm going to do something to make life a little easier because I know what I want. You wouldn't necessarily know to do this, but I'm going to do it. So I'm going to multiply everything through by a negative 1. So I'm going to make this negative natural log p plus a natural log of m minus p minus kt, and it doesn't matter that c is c because c is going to change depending on whatever it is, so that's okay. Now the reason I want to do that is for my log rules, because I want to make this the natural log of the absolute value of m minus p on top and p on the bottom. equals negative kt plus c. Now I can e both sides, and I know that on the left I will just have the absolute value of m minus p over p, and on the right I will actually have e to the negative kt times some constant. Well, we're going to call that constant a instead of c. Okay? So it's a e to the negative kt. Hopefully that makes sense. And since p sub 0 is your initial population, and the carrying capacity minus the initial population divided by the initial population really comes from, if you think about this formula, a e to the 0, because initial means 0. That means that really that's equal to a. In other words, m minus initial population over the initial population. So that's really what a is. It doesn't really matter that you just need to know that that changes to a. It's still a constant, okay, for our purposes. All right. So, and I know that that a is going to change signs depending on whether or not I need a positive or negative there. So I'm going to just say it's a positive. So I'm going to get rid of the absolute value, in other words. I'm going to say that this is really m over p minus 1 equals a e to the negative kt. So I got rid of the absolute value. I split this up into two separate fractions. So I can say then that m over p equals a e to the negative kt plus 1. Well, I don't want m over p, I want p over m. So I'm allowed to flip both sides of an equation. It doesn't matter whether they're both on top or both on bottom. So I'm going to flip both sides. I'm going to say that's p over m equals 1 over a, actually I'm going to rewrite it as 1 plus a e to the negative kt. And now I'm going to multiply by m, and so my population equation is m over 1 plus a e to the negative kt. So you'll notice that the k comes from the differential logistic equation. The a is something you have to solve for based on your initial condition. Okay? So you have to solve for that based on your initial condition in the population equation. But m is your carrying capacity, which you know, and k comes from your differential equation. So you get everything from the differential equation, basically, except for the a, and you have to plug in your initial condition to do that. Now, I wouldn't expect you to do that on an AP test, to go through and develop that, but that is really why you learn partial fraction decomposition, because it's how a logistic growth differential equation is solved. So that's what it is. So how are we going to use this? How are the questions going to be asked that we're going to have to be able to answer? Well, let's look at some examples. Okay, number 1. The growth rate of a population of bears in a newly established wildlife preserve is multiplied by the differential equation dp over dt equals 0.008p times 100 minus p, where t is measured in years. Well, if you remember, I told you that the logistic differential equation we wanted was of the form dp over dt equals kp times the quantity 1 minus p over m. So I have to have this first term be a 1. So in this differential equation, what would I need to do to make that first term be a 1? Well, I would have to divide by 100, which means I'd have to divide in here by 100. I have to divide both terms by 100. Well, if I'm multiplying by something, and if I multiply by 100 and divide by 100, I really haven't changed the value of anything. So what I get then is dp over dt equals 100 times 0.008 moves the decimal point 2 places to the right, so 0.8p times 1 minus p over 100. So why is that helpful? Because in that form I can read what the carrying capacity is. The carrying capacity, or your constraining value, but they call it carrying capacity, would be 100 bears. So the environment in which they put the bears can only support 100 of these wild bears. What is the population of bears when the population is growing the fastest? So it's growing the fastest at half the carrying capacity. So that would be when you have 50 bears. What is the rate of change when the population is growing the fastest? So part C asks us, what is the rate of change when the population of bears is growing the fastest? So in that case, I am wanting to know what dp over dt is when p equals 50. So I would say dp over dt would equal, I know that's 0.8 times 50 times 1 minus 50 over 100, which is just a half, and 1 minus a half is a half. Half of 50 is 25, so it's 0.8 times 25, which would be 20 bears. So you'd have 20 bears per year when it's growing the fastest. Let's look at another example. In 85 and 87, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario, to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach the carrying capacity in about 25 years with a growth rate given by the differential equation. According to the model, what is the carrying capacity? First of all, I'm sure the most important question you have is, what is the plural for moose? It is not meese, it is moose. I looked it up. It always becomes a talking point when we do this problem. Anyway, so what's the carrying capacity? Well, I have to rearrange this differential equation in order to see the carrying capacity. So dp over dt is going to equal, so I'd have to divide the 1,000 by 1,000 and the p by 1,000, which means I'd have to multiply by 1,000, and that's 0.003p times 1,000 would make it 0.3p. So we'd have 0.3p times 1 minus p over 1,000. Now we can read what the carrying capacity is, and it would be 1,000. Now they're asking us to solve the differential equation with initial condition p of 0 equals 61. So now they want me to find the differential, solve the differential equation p equals m over 1 plus a e to the negative kt. So what do we know? Well, we know we're solving for p, so p equals, we know the carrying capacity is 1,000 over 1 plus a e to the negative, k is going to be 0.3 t. Okay? Well, they tell us that p of 0 is 61. So if I say 61 equals 1,000 over 1 plus a e to the 0, that'd just be 1 plus a. If I multiply both sides by 1 plus a, I'd have 61 times 1 plus a, so I'm going to divide by 61. So I have 1 plus a equals 1,000 over 61, or a equals 1,000 over 61 minus 1. So if I were to find out what that is in my calculator, I get 15.4. So that means my differential equation with the initial condition p of 0 is 61. So if I start with 61 moose, that my population equation is going to be 1,000 over 1 plus 15.4 e to the negative 0.3 t. So I can tell what the population will be at any time given this population model. Okay? Continuing on, oh, I thought there was more to that question. I guess that's it. All right, so continuing on to the next example. Now we're talking about biologists stocking a lake with 400 trout and estimating the carrying capacity to be 10,000. Observation of the trout in the lake revealed that the number of trout tripled in the first year. Assuming the size of the trout population satisfies a logistic growth model, write the differential equation for your model and an expression for the size of the trout population P after T years. So I want dP dt and I want P. That's what they're telling me to find. Okay? They're telling me that P of 0 is 400 and that the carrying capacity is 10,000. Okay, so actually, I'm sorry, they use an expression for the size of the trout population P after T years. Oh, so I'm looking for K. So I don't have to find dP dt, although I kind of have to. Nope, I don't. I just need P. So remember that our formula is P equals M over 1 plus AE to the negative KT. So what do we know? We know we have P equals 10,000 over 1 plus AE to the negative KT. Hang on. To the negative KT. So I have to find both K and T and A. All right, well, I'm given this initial condition of 400. So I know that when I start with 400 in my population, that would be 10,000 over 1 plus A e to the 0. So I know that 1 plus A is going to equal 10,000 over 400, or that A is going to equal 10,000 over 400 minus 1, which is 24. So I now know that P equals 10,000 over 1 plus 24 e to the negative kt. All right, so now I have to find K. Well, they do tell me something else, and that's the population tripled in the first year. So if we start with 400, tripling would mean we'd have how many? Well, 3 times 400 would be 1,200, and that would be when t equals 1. So P of 1 is actually 1,200. So 1,200 equals 10,000 over 1 plus 24 e to the negative k, because t was 1. So now I can solve for k. So again, I'm going to divide by, I'm going to multiply by 1 plus 24 e to the negative k and divide by 1,200. So I'll have 1 plus 24 e to the negative k equals 10,000 over 1,200. So I'm going to subtract 1. I'm actually going to divide by 24. So that's e to the negative k. So I will take the natural log of both sides. So I will have negative k equals the natural log of 10,000 over 1,200 minus 1 all over 24. It is important to not round until the last step so that you get a better answer. And then I actually will change my signs. So when I type that in my calculator, I do get a negative value for the ln, but then because that's a negative k, that means it's 1.1856. Okay? So that would be my population growth constant. All right. Now, part B says, what will the trout population be when the rate of growth predicted by the logistic model changes from increasing to decreasing? So that's the point of inflection, which is half the carrying capacity. And if the carrying capacity is 10,000, that will be a trout population of 5,000. So that's a pretty easy question. Next, find the value of the largest rate of growth for the trout population. So, that means when P equals 5,000, the largest rate of growth would be dP over dt. So that would be Kp. So we know that K, let me write that up here, dP over dt equals Kp times the quantity, 1 minus P over M. So dP over dt equals K, which is 1.1856, times P, which is 5,000, times 1 minus P, which is 5,000, over carrying capacity, which is 10,000. Remember, that's just 1/2, because that's 1/2, and 1 minus 1/2 is 1/2. So half of 5,000 is 2,500 times 1.1856. We get dP over dt is 2,964. And so that would be the rate of growth for the trout population when its largest rate of growth would be 2,964 trout per year. Okay? Then it says, after how many years with the rate of growth of the trout how many years will the rate of growth of the trout population change? In how many years, or after how many years will it change from increasing to decreasing? Show your work. So that means I want to know T in the population equation. So population is m over 1 plus AE to the negative KT, and we want to solve for T. So again, we know that this is 5,000 when that's happening, equals 10,000 over 1 plus, we found A to be 24, and we found K to be negative 1.1856 T. So I have to solve for T. So I multiply by 1 plus 24, e to the blah, divide by 5,000. So I know that's 2. Right, because 10,000 divided by 5,000 would be 2. So we'd have 2 minus 1 would be 1 divided by 24. So we'd have e to the negative 1.1856 t equals 1 over 24. Now I take the natural log of both sides. So I get negative 1.1856 t equals the natural log of 1 over 24. So we end up with t equals 2.6819. So after how many years does it, so when is the point of inflection is actually what that's asking me. And that would be at 2.6819 years. Okay? All right. E. What is the limit as t approaches infinity of P of t? So that means that's your carrying capacity. That's another way of asking what's the carrying capacity. So that's an easy question. That's just 10,000. Okay? F says, set up an equation to find when the trout population will reach 8,000 and use your calculator to solve. All right, so that means I'm using my population equation. So 8,000 is what I want my population to be. carrying capacity is 10,000 over 1 plus 24 was A, e to the negative 1.1856 t. Now it says to use my calculator. So I'm going to enter that in y1. I'm going to enter that in y2, except I'm going to enter t as x. I'm going to graph them, and I'm going to zoom 0 to see where they intersect. Intersection point is approximately 3.8485. Don't forget, we are writing 4 decimal places in this class, okay? So the population will reach about 8,000 in about 3.8 years, almost 4 years. All right, so just kind of to boil things down. You need to recognize when you see a differential equation, when it's of this form, when you have 2 variables like that, that it's a population, logistic population differential equation. Not all of them are, okay? Not all of them are. And that whenever I solve for it, that's the formula that I will use. A is the constant determined by your initial population, M is your carrying capacity, K is the growth constant, and T is time. Hopefully that makes sense, and you were able to fill in all of the notes. I am putting 1 practice problem on Schoology in case if you would like to just run through it. I did not print it out for you, so that will be up to you as to whether you want to look at it, but we will look at the solution together in class the next time I see you. So if you want to go ahead and take a glance at it, that might not be a bad idea.